Hi, and welcome back to MSc. In today's lesson, we're going to look at Le Chatelier's principle, specifically looking at the effects of an addition of a catalyst on the position of the equilibrium. So here, once again, we have our equilibrium reaction. We have a position of the equilibrium saying we have more products at equilibrium than we will of reactants. Again, it's not amounts that we're concerned about, it's the rate forward and rate backwards being equal at equilibrium. We have our Kc equation down here for the equilibrium constant. So in order to understand what a catalyst will do to an equilibrium reaction, we need to go back and think about what a catalyst does. And so a catalyst is going to increase the rate of reaction by lowering the activation energy. So if we look back at some of our energy or potential energy profiles, rather, we have energy and we can have the extent of the reaction along the x-axis. Our potential energy profiles might look something like this, where we have a profile that looks like that, and we have our reactants up at this level, and we have our products down below. And we have our activation energy being the difference between this point here and the top. The catalyst will come along, and the catalyst will lower that. So it'll make the energy required to do the reaction less. But notice this as a forward reaction here, this would be an exothermic reaction, because you'd have a decrease. This would be your delta H down to this bottom level here. There's your delta H. And the reverse reaction would be endothermic. So if we picture that reverse reaction going back this way, that would be endothermic, that reverse reaction. And so we can notice that regardless which way you approach this, the decrease, the difference between what used to be the top of the energy curve and the new top has been reduced the same in both directions. So as it turns out, the catalyst will lower this activation energy in both directions. And it's really important to state that that happens equally in both the forward and reverse reactions. And so by lowering this amount equally in both the forward and reverse reactions, well, that then means that it's not going to actually change the position of the equilibrium at all. The equilibrium will stay at the exact same spot. What it would mean is if I hadn't yet reached equilibrium, it would reach equilibrium faster. That's all. It won't change the position. It certainly won't change Kc. As we've seen, only temperature will do that. And it won't change any of my equilibrium concentrations at all. All it will do is get me there faster. When you're answering the question, though, you do want to say that it affects the activation energy or the rate of the forward and backward reactions equally and makes them both faster. But as we know, for an equilibrium, we have equal rates. And so if it's increasing both rates equally, it will not change the position of the equilibrium at all. And so when we add a catalyst, it's almost like a bit of a trick question. And as long as we're stating that the forward and reverse reactions rates increase equally, we've covered ourselves. Kc is not going to change, and we've answered the question fairly fully at that point. So, to recap, catalyst will have no effect on the position of the equilibrium or on the value of Kc because it changes the rate of the forward and reverse reactions equally by lowering the activation energy equally in both directions. Hope you found this short video helpful. Thank you for listening, and thank you very much for watching.